Hey everyone, so we're going to start with with doing some problem solving stuff today, and there are sort of a couple different things that I want to look at. So this week we looked at three new sections. We looked at the chain rule, we looked at directional derivatives, and we began looking at optimization, and critical points. So we're going to do a little bit of all of those. So let's start off with the chain rule. So some problems involving the chain rule. And the basic principle here is if you've got some function f, I don't know, let's call it fxy, and you've got x as some function of t and y is some other function of t, then what that tells you is that really f is a function of t as well. So you can differentiate f with respect to t, and what you get is exactly what you expect you'd get. You would get dx dt del f del x plus dy dt del f del y. And it carries over to any number of variables. So let's do a simple problem with something like that. Let's say that we've got z is going to be equal to sine x times cosine y. X is equal to tangent of t, and y is equal to arctangent of t. And we want to know with all of this information, what's dz dt? That's the problem. Now, for these kinds of exercises, what I like to do is, as a first step, is just write down what the chain rule is. The chain rule we need, and the chain rule we deserve right now, tells us that dz dt is del z del x, right? You're changing x a little bit, but x depends on t as well, so dx dt. And then the same thing with y. You change y a little bit, and then you get dy dt. So you need all of these. A good first step is to just take stock of everything that you may possibly need, and you're going to need all of these. So with that in mind, let's actually figure out what some of these things are. So dz dx, or del z del x, rather, del z del x, we can see that that's going to be cosine x cosine y. Del z del y, meanwhile, is going to be negative sine x sine y. We also need to know dx dt. Dx dt is going to be secant, the derivative of tangent is secant squared. That's a simple quotient rule. And then dy dt, this is one of those things you just kind of have to know. Arctangent of t is 1, you differentiate that, you get 1 over 1 plus t squared. And if you're not familiar with that, then you can show why that's true using a trig substitution. But if you do remember that, well, good. That's a thing you need to remember. That's an important derivative. And that's basically it. We're almost done. So the upshot of all of this is that the derivative, dz dt, just multiply all of them. That's going to be del z del x times dx dt. That comes out to secant squared t times cosine x cosine y minus 1 over 1 plus t squared sine x sine y. Now, strictly speaking, if you wanted to, you could take this a step further and write, let me actually just say, first of all, this is a perfectly fine answer. There's absolutely nothing wrong with leaving your answer this way. It's actually quite nice. But technically, that's the same thing as saying secant squared t cosine of, now x you know is tangent t times cosine of arctangent of t minus 1 over 1 plus t squared times sine of tangent t times sine of arctangent t. If you want, you can leave it in this form as well, but there's no real advantage to doing that. And as you can see, it gets pretty ugly pretty quickly. So it's fine to leave it in our box answer. There's absolutely nothing wrong with that. Okay. So let's do another example. You can do this in any number of variables that you want, like I said. So let's say, for example, we want to take, here's something else. Let's take, for example, z is equal to ln of 3x plus 2y. Let's say that x is equal to s times sine of t, and y equals t times cosine of s. Now, in this case, by the way, I didn't do this before, but you can write what's called a tree diagram. So in this case, this just gives a diagram to show all the dependencies. Z, you know, depends on x and on y. X, meanwhile, we know depends on s and t, and so does y. Y also depends on s and t. So here's the advantage of doing this. Here's the advantage of using something like that. That makes it very easy to now then say, so suppose we want to find, let's do both. Let's say we want to find del z del s, and we also want to find del z del t. What are those things? Well, let's start off with del z del s. If you follow the tree diagram, you're going to go down to del z del x and then del x del s. That leads you down to, so I'll just repeat that, del z del x times del x del s plus, and then you're going to go down the y direction in the same way. So that's going to be del z del y del s. But meanwhile, if you want to find del z del t, well, del z del t is very similar, but in this case, you're going to go down the z direction and then go from x to t. Again, go down the z direction and go from y to t. So in that direction, you're going to find that it's going to be del z del x del t plus del z del y del t. So once again, we're going to need to know all of these things. So let's start off finding del z del x and del z del y. Del z del x in this case is going to be 3 over 3x plus 2y. Del z del y, very similar, 2 over 3x plus 2y. Del x del s, we know, is going to be just sine of t. Del y del s is negative t sine s. And while we're at it, why don't we also just find del x del t, which is s times cosine of t, and del y del t, which is cosine of s. The upshot of all of this is that we can now conclude that del z del s is the same thing as, let's see if we can just do it all together. Del z del x times del x del s is 3 over 3x plus 2y times sine of t minus 2 over 3x plus 2y times t sine of s. And meanwhile, we know that del z del t, similar principle pretty much. Del z del t is going to be 3 over 3x plus 2y times, now in this case you're going to need del x del t, which we said is s times cosine t plus 2 over 3x plus 2y times cosine of s. And that's it. Those are your two partial derivatives. So that's about all there is really. That's really to it. So in that sense, it's pretty simple. You just have to keep careful track of all of the derivatives that you're doing basically. But that's pretty much all there really is to it. Okay. So let's do something else. Let's say that now there are a couple. Now, what are some ways that this can get a little bit more interesting? Well, one way they can get interesting. Here's a nice little problem. So let's say that we know that f is some function of x and y. And we know that's a differentiable function. And we know that g, we've got some other function, g u v, is equal to f times, not times, oh wow, f of e to the u plus sine v and e to the u plus cosine v. And what else do we know? We're given a table. So table of values. This is a problem in Stewart, by the way. The table of values that we're given is you've got. I'll draw it out. It's so it's got 3 columns and or two. Really, it's got 2 columns and 4 rows. Excuse me, other way around. 4 columns and 2 rows. And basically, what this looks like is you've got 0, 0, and you've got 1, 2. These are the values for the point you're evaluating. You've got f, g, fx, and fy. And we're told in this case, I'm going to do this in green, we're told in this case that f of 0, 0 is 3, g of 0, 0 is 6, fx of 0, 0 is 4, fy of 0, 0 is 8, fx of 1, 2 is 6, g of 1, 2 is 3, fx of 1, 2 is 2, fy of 1, 2 is 5. So here's how you use this table. What this table means, basically, is that, I'll just repeat what I just said, f0, 0 equals 3, g of 1, 2, to find g of 1, 2, that's going to also be 3, and fx of 0, 0 is 4, and so on and so on. So that's how we're going to use this table to figure out what all these different values are. And what we want, here's what we want to find. What we want to find is GV, or GU, 0, 0. And we want to find GV of 0, 0. Now these are nice problems. So what we can do here is we can say, okay, well, we know that G of U of V equals f of x and y when we say that x is e to the u plus sine v and y is e to the u plus cosine v. So I don't know, let's say that we're going to let GUV equals z. Then what we really want in that case is we want to know del z, del u at the point where uv equals 0, 0. And we want to know del z, del v at the point where uv is equal to 0, 0. That's what we're really looking for. Now, del z, del u is del z, del x, del u, plus del z, del y, del u. Now, del z, del x, if z is equal to guv, that's also equal to fxy. Which means that if you're differentiating z with respect to x, what that really means is you're taking fx of whatever x and y are, I don't know what they are, at the point, you're taking fx, xy at del x, del u. Now del x, del u, if x is e to the u sine plus sine v, then del x, del u is just e to the u. Plus, now similar story, fy, xy. Now del y, del u is once again e to the u. Now at u equals 0 and v equals 0, we have that x is e to the 0 plus, what was that? E to the 0 plus sine of 0, so that's just 1. And again, that's e to the 0 plus sine of 0. And y is equal to 2, or in other words, e to the 0 plus cosine of 0. So in other words, what this really becomes is fx at 1, 2 times e to the 0 e to the, wait a second, yeah, e to the 0 plus fy 1, 2 e to the 0. And if we look back at our table, fx of 1, 2, you see that xf of 1, 2, well, that's just going to be 2. And e to the 0 is of course, just 1. Plus fy of 1, 2, which we see as 5. So the answer is 7. And a similar thing will happen when we take del z, del v. That's going to be del z, del x, del v, plus del z, del, not x, I'm sorry, del y, del v, which just comes out to, which is just going to come out to del z, del x. We already know that. That's going to be f x, xy. Now, del x, del v in this case is cosine v minus minus fy xy sine v. And in other words, what that really is going to come out to is fx, we already saw this, that's 1, 2, cosine of 0, minus fy, 1, 2, sine of 0. But that sine of 0 term is going to go away because sine of 0 is just 0. So really what this becomes is fx of 1, 2, because cosine of 0 is 1, and fx of 1, 2, we already know that that's just 2. So that's it. That's how this works. Now you may notice, you may ask yourself, well, wait a second, we didn't use that entire table. There's lots of information there that we didn't use. Yes, that's true. This is an interesting problem because it really forces you to think about what information do I need and what information is actually superfluous. Like I didn't need to know what f of 1, 2 was or what g or what fx of 0, 0 was. It gave us that information, but we had to decide for ourselves what information was important. So it's good to be aware of what information is really important as you're going through these kinds of problems. Okay, so what else is there? let's do one more of these. By the way, tomorrow during recitation, I'm going to do some application problems with some of these things. So we'll look at that a little bit tomorrow as well. But for now, what if I say that we want to find, here's another good example, applications and also implicit differentiation. What if we have z is equal to x to the fourth plus x squared y? You know that x is s plus 2t minus u. Y is stu squared. Again, we've got a tree diagram, but this time the dependency is a little bit different. Z depends on x and y still, but x and y each depend on three things, s, t, and u. So in this case, we're given some other information. We need to know, we want to find del z del s, del z del t, and del z del u at the point where s is equal to 4, t is equal to 2, and u is equal to 1. Now, it's always a good idea whenever you're given these variables for some start off, it's always a good idea to figure out what x and y have to be, what your intermediate variables are. So x in this case, s is 4, so that's 4 plus 2 times 2 minus 1, or in other words, 7, 8 minus 1. And y, meanwhile, is 4 times 2 times 1 squared, or in other words, 8. Let me try and make that 8 a little bit more neatly written. There we go. So that's good to start. Now, del z del s is del z del x del x del s plus del z del y del s plus del z del, oh, nope, that's it. That's all there is for this one, fortunately. Maybe I should do an example next time with some more variables. So we need to know what all these things are. And again, that's just going down the tree diagram as before. So with all that in mind, what we can conclude from that is we need to know what del z del x is. Del z del x is going to be 4x cubed plus 2xy. And plugging in these values for x and y, that's going to become del z del x at xy equals 7, 8. And that's 4 times, oh boy, 7 cubed. I don't want to have to do that. I guess I didn't pick these numbers very well. But that's okay. 7 times 7 is 49. 49 times, okay. This comes out to 4 times 343 plus 2 times 7 times 8. And what that becomes, after going through this, 4 times 343, 4 times 2, so 2 times 343. This is going to come out to 1,372 plus 14 times 8, 7 times 8 is 56. 56 times 56 times 2 is 112. Or in other words, 1,484. All right? Now, meanwhile, you can also go down the other directions. We would have del. Oh, wait a minute! I didn't finish the problem yet. What am I doing? So the so now that we know what del x del z is, we're also going to need to know del y del z. Actually, yeah, I'll do it back here. Del y del z, which in this case is going to just be much simpler. That's just x squared. And x squared, that's going to give us del. I'm now looking at this and I'm realizing that I inverted my y and my z. That's odd. Del z del y. So del z del y at the point where xy equals 7, 8. Well, that one's much simpler. That's just 49. Now we also need to know del x del s. Del x del s is 1. Del y del s is tu squared, or 2 times 1. That's just going to become del y del s at 4, 2, 1 is equal to 2. For posterity, let's just finish this. We can say that del x del t is always going to be 2. Del y del t is su squared, which comes out to 4 when we plug everything in. And del x del u is -1. Del y del u is 2 stu, which comes out to 16. So after putting all of this together, we get del z del s is del z del x del s, or in other words, 1484 times 1 plus 49 times 2, or in other words, 1484 plus 98, which comes out to 1582. Now let's go in the opposite direction. Let's go in another direction. Let's say we're going to look at del z del t. Now you're going down z, then t, and y, and t. Del z del t is going to be 1484 del x del t, which is 2, plus 49 del z del y del t, which is 4. Going through that, that's going to become 3,164. And finally, I'm going to just do one more of these. Let's see, I'm going to go, I'll make this one purple. That's too similar to that one. I'll make it green. So finally, going down the u direction, we can say that del z del u is going to be 1484 times del x del u, which is -1, plus 49 del y del u, which is 16. Or in other words, -700. All right, so there are our solutions. That's about it. So, so the point here is that working the chain rule is not really excessively difficult. You just have to really keep your head on straight and make sure you're going through all of the right calculations as you're doing this. So hopefully this elucidated a little bit of what was going on here. Okay, so let's move on. Well, I want to move on to looking at directional derivatives and things like that. So now, what if we have, so this is now the next thing that we're looking at. Directional derivatives in the gradient. Now, most of what I'll do today is just going to be just looking through some calculations, but not tomorrow. on Friday, I'm going to be doing some more interesting geometry problems involving these. So if you're having trouble understanding what these things are geometrically, then make sure that you tune in on Friday. So, but I'll look at some general things to look at today. So what if we start, I want to start off by suggesting, what if you have, here's a problem. Actually, hold on. So we can take f xy, that's going to be y times cosine xy. Find the derivative at the point 0, 1 with angle pi over 4 above the, with angle pi over 4 from the I direction. So the image we should have in our mind as we're looking at this, at the point 0, 1, so that's the point that we're at, and we're looking at this vector. We're looking in that direction, right? And we're assuming that this angle is pi over 4. So we want to know what that vector is. Now, what do we need? This is a directional derivatives problem, and it's always good to write down the formula for directional derivatives. And this is one of the most important formulas that we'll look at in, I forgot something important. The gradient of f dotted with u. This is one of the most important formulas that we'll look at in the entire semester. Certainly, if you're taking 231, this is, I think, one of the most important that we'll look at, period. So so what do we need? We need to know what the gradient of f is. The gradient of f, in this case, it's just the vector of partial derivatives. And that's going to come out to, so the derivative with respect to x is negative y squared sine xy. Derivative with respect to y is cosine xy minus xy sine xy, which means in particular that the gradient at the point 0, 1 is given by 0, comma, and 0, 1, I think, because in the y direction, in the x direction, that's, sine of 0 is 0, and in the, so sine of 0 is 0, and then cosine of 0 is 1, so yeah, that looks right. So, but what about u? U is the unit vector that's pi over 4 above the x-axis. In other words, it's this guy, right? These are the same vectors that I've just drawn. There's your u, and assuming that I'm a good artist, which I'm not. So, but the idea is that that's an angle of pi over 4 above that axis. Now to do that, well, just think about what that means. That vector is going to be parallel to actually, how do I want to say that? Let's zoom in a little bit. If we zoom in a little bit, here's the vector u. Here's your angle of pi over 4. And we know that it has to be a unit vector, so its total length is 1. And now that we've drawn this figure, this looks like a pre-calc thing. We've got the points 1 over root 2, 1 over root 2. So we can conclude, at this case, that u actually is just going to be 1 over root 2, comma 1 over root 2. That will do the trick. So what our upshot here is the derivative in that direction at the point 0, 1 is the gradient, which is 0, 1, dotted with the vector 1 over root 2, comma 1 over root 2, or in other words, just 1 over root 2. It's about all there is, really. That's about all there is to it. Let's do another example. What if we want to look at, what if we want to look, I don't know, let's say that we're going to look at the vector, or we can do this in 3 variables also. Let's look at fx, y, z. Fx, y, z is going to be xy, sorry, let's say that this is x squared y plus y squared z at the point 1, 2, 3. In the direction v given by 2, -1, 2. Here's what you don't do. So first of all, we want to again find the derivative at the point 1, 2, 3 in the direction of v. So here's what you don't do. What you don't do is you don't say that this is the directional derivative like so, that you're going to take the gradient of f at the point 1, 2, 3 dotted with v, the vector, 2, -1, 2. And the reason you don't do this is because this vector, that's not a unit vector. And it's very important as we're doing this problem, as we're doing any kind of these directional derivative problems, it's very important that that vector is a unit vector. So you can't do that. That's not our first step. Always look at what the equation in question actually is. duf at the point 1, 2, 3 is the gradient of f at the point 1, 2, 3 dotted with the vector u. So what is the vector u? Well, we don't know, but all we know is that u is in the same direction as v. And of course, importantly, use a unit vector, so the magnitude of u is 1. What that means is that u, we've seen how to do this, is just v over the magnitude of v. Right? So the magnitude of v is the square root of 4 plus 1 plus 4, or in other words, that's root 9 or 3. So u we can just write as 1/3, oh, sorry, 1/3 to -1, 2. Meanwhile, the gradient of f, if you just go through this process, 2xy, x squared plus 2yz, differentiate with respect to z, you get y squared, which means that the gradient of f at the point 1, 2, 3, 2 times 1 times 2, or in other words, 4, 1 plus 2 times 2 times 3, so 1 plus 12 is 13. And then y squared is going to be 4. So that's about all there is to that. Now you can dot these. Now we're ready to say that du f1, 2, 3. Well, it's going to be 4, 13, 4, dotted with 1/3 times 2, -1, 2. Here's a little trick you can do, by the way. You can write that as 1/3 and then do this dot product. You can bring the 1/3 out front. There's no problem with that. So that's going to be 8 minus 13 plus 8. Or in other words, 16 minus 13 over 3, or in other words, 3 over 3, or just 1. There's our answer. Our answer is that it's changing with a direction of 1. Now here's another question. So here's part 2 of this question, which is, what is the maximal rate of change? What's the maximal rate of change? And what's its direction? and direction thereof. Well, the direction of the maximum rate of change is just the gradient of f at the point 1, 2, 3. And we know what that is. That's going to be 4, 13, 4. You don't have to make it a unit vector because all we really care about is direction, so it doesn't matter how we scale it. That's fine. But the magnitude is going to be the magnitude of the gradient, which in this case is 16 plus 16 plus 169. Or in other words, so 132 plus 169, which comes out to this to root 201. So that's the maximum rate of change. Let me actually rephrase some of what I wrote here to accommodate that. That's the maximum rate of change. So the direction of the maximum rate of change is always the gradient, and the maximum rate of change itself is always the magnitude. Little trick. Okay. So what else? Let's see. So again, tomorrow I'm going to do some. Let's see. Should I do this now or should I do it tomorrow? I'll wait to do some of those other things tomorrow. So for now, I'll move on to classifying critical points. Now, this is a little bit of, this can be a little challenging for some folks. And so here's the main gist behind classifying critical points. So actually, let me rephrase this. I'll write this as finding in classifying critical points. And there are really two steps to this. The first step is to find all points x, y, where you have that the derivative, both partial derivatives are equal to 0. And this might seem obvious, but you have to make sure that those are equal to 0 simultaneously. It's not going to work if you say, okay, well, here's some x and y that make fx equal 0. Here's another x and y that make fy equal to 0. No, they have to be 0 at the same time for the same values of x and y. And the second step to classify with what's called the second derivative test. And the second derivative test, to remind everyone, you define this new object called the Hessian matrix, or the Hessian determinant, which is fxx, fxy, fyx. Again, those are usually the same thing, fyy, which in other words becomes fxx times fyy minus fxy squared. And three different things can happen. On the one hand, you could have that fxx at your critical point xy is greater than 0, and actually that's usually not how you start off, is it? Let me rephrase that. You could have that the Hessian is positive and fxx is positive, and if it's positive, Positive means it's a local minimum. You could also have, that the Hessian is positive, but the second derivative of x is negative, which means it's a local max. So far, this is very much like what happens in Calc 1, but here's where things get a little different. You could have that the Hessian is negative, and if the Hessian is negative, it's a saddle. Last possibility is if the Hessian is actually equal to 0, and that doesn't happen often. It's not going to happen almost at all in our class, but if it does, then this test is inconclusive. But let's look at a concrete example of this. Let's say that we've got fxy. I don't know, we'll start off simple. Fxy is x squared plus xy plus y squared plus y. And we want to find and classify the critical points. Well, we start off by taking the by taking just the regular derivatives and setting them equal to 0. So that's 2x plus y. That has to be 0. We also know that y plus 2y, x plus 2y plus 1 is equal to 0. And we have to solve these equations. Well, this first equation, how might we do this? Well, one thing we notice is this first equation can be written as y equals negative 2x. And if y equals negative 2x, that means we've got x plus 2 times negative 2x plus 1 is 0. That's from the second equation. Or in other words, that's x plus negative 4x plus 1, or 1 minus 3x equals 0. Or x equals 1/3. And if x equals 1/3, that means y has to equal negative 2/3. That's our only critical point in this case. It's the only one. So there's only one of them. Now, how do we classify this? Well, fxx is a constant function 2. Fyy is also a constant function 2. Fxy is a constant function 1. Those three, that triple equal sign means is constant. It's a constant function. And what all of that tells you is that our Hessian, which is fxx fyy, minus fxy squared, well, that's also constant. It's 3, which is clearly always positive, and in particular positive at this critical point. And fxx is always positive. So if we look back at our second derivative test, we can see that that means that the point 1/3, negative 2/3 is a local minimum. Now that's a relatively simple example. Let's look at something a little more complex. What if we take fx y is equal to x minus y times 1 minus xy. Same exercise. So in this case, we're going to find them first. Fx, this is just the product rule. 1 minus xy minus y times x minus y. And if you do that out, that becomes 1 minus 2xy plus y squared. And that has to be 0. Fy, meanwhile, is going to be, that's a similar exercise. In this case, it's going to be negative 1 minus xy minus x times x minus y, which in this case is going to come out to -1 plus 2xy minus x squared equals 0. Now this one's a little more complicated. It's more complicated because you can't just isolate a single variable anymore. There's no obvious way to say, oh, well, x equals blah in terms of y. It's not obvious how you would do that. In fact, I don't actually think you can do that in a reasonable way in this case. But what we can do is we can write this now. We can look at these guys and we can just take these two equations. Let's just summarize for a second. So we've got y squared minus 2xy plus 1 is equal to 0. Negative x squared plus 2xy minus 1 equals 0. One thing we can do is we can add these equations together. If we add them together, the 2xy's and the 1's cancel, and we're left with y squared minus x squared equals 0. So y squared minus x squared equals 0, which tells us that x squared is equal to y squared. Now, that does not necessarily mean that x equals y. It could be that x equals negative y, so there are two things that can happen. There's either x equals y, or there's also, I'll do this over here, x equals negative y. Let's start off with the x equals y case. If x equals y, then the first equation becomes x squared minus 2x squared plus 1 is, well, okay, that's negative x squared plus 1 equals 0, which means that x squared equals 1. And if x squared equals 1, that means that x equals plus or minus 1, which means that y equals plus or minus 1. That leaves us with the critical points 1, 1, and negative 1, negative 1. But what if x equals negative y? If x equals negative y, then that means that we have, oh, and by the way, those also work in that 1, 1 and that negative 1, negative 1. You can observe for yourselves that that will also work in the second equation. You didn't have to do it the first one. In fact, the second equation in this case is just negative 1 times the first one. But what about if x equals negative y? If x equals negative y, then y squared is still x squared. So that becomes x squared plus 2x squared this time, because x equals negative y plus 1. Or in other words, 3x squared plus 1 is 0, which means that x squared is equal to negative 1/3. Now, there's a problem with this. There's a really big problem here. The problem is that can't happen. We look at this and we say, wait a minute, there's a problem here, which is that x squared has to be greater than or equal to 0. Of course it does, because it's a square number, and squares are always positive. So did something go wrong here? Well, let's check. Let's make sure that this is okay. Well, we calculated the derivatives correctly. We're certain of that. And if you plug in x equals negative y for y, or y equals negative x, well, y squared is still x squared, and negative 2xy becomes positive 2x squared in that case. So yeah, everything seems to check out. What went wrong? Well, nothing went wrong. It's just that we found that that can't happen. So the upshot of this is that x cannot possibly be equal to negative y. That can't happen. So that leaves us with only two critical points, 1, 1, and negative 1, negative 1. Now let's classify them. fxx, in this case, becomes negative 2y, fyy becomes 2x. I'm sorry. fxy, you differentiate x with respect to y, fx with respect to y, and you're going to get 2y minus 2x, which is the same thing that you get if you differentiate fy with respect to x. So the upshot of all of this is that d is equal to negative 4 xy minus 4 times y minus x squared. That's what you get when you take y squared, that's what you get when you take fxx, fyy, minus fxy squared. Well, d11 in that case is going to be negative 4, which incidentally is also d negative 1, negative 1. Both of which are obviously negative. So the answer in this case is 1, 1, and negative 1, negative 1 are saddles. There's our answer. Now I want to point out, by the way, something that we didn't do. What we didn't do is we didn't write, this is something to be cautious about. We didn't write plus or minus 1 comma plus or minus 1. Technically we could have, but that's often misleading because that's often misconstrued to mean 1, 1, negative 1, negative 1, 1, negative 1, and negative 1, 1. But 1, negative 1, and negative 1, 1 are not critical points. We saw that before, that we can't have it be the case that, that x and y are of opposite signs. That was one of our major conclusions here. Okay, so with all that in mind, I just wanted to point that out there. And again, you can still write this as plus or minus 1, but you have to be very careful when you do that to make sure that your signs are all straight. Okay, let's do another one of these. Let's say that we take fxy is equal to x squared plus y to the 4th plus 2xy. Well, in this case, as we're trying to find and classify the critical points here, fx, 2x plus 2y is equal to 0. And fy is 4y cubed plus 2x equals 0. Now that's a good way to start because what that means in particular, we can see from the top equation that that means that x has to be equal to negative y. And if x is negative y, then that means that this lower equation becomes negative 4x cubed plus 2x is equal to 0. Now again, here's what you don't want to do. Here's what you want to be very careful about doing. That implies that 2x equals 4x cubed, which means that x equals 2x cubed, which means that 2x squared is equal to 1, which means that x squared is 1/2, which means that x is plus or minus 1 over root 2. The problem with doing this is at this step right here, at this stage. Because at that stage, what if we have that x is equal to 0? If x is equal to 0, then we just divided by 0, and that's not going to work. That's a problem. And if you stare at these two equations, you'll notice, actually, yeah, x equals 0 is a distinct possibility. How can you avoid this? How can you just completely, now you might be thinking to yourself, oh man, you're telling me that if I ever divide anything, I have to make sure that it's not 0? Well, yes, But how do you keep track of that? Is there a better way to do this? Well, to avoid this issue, and this is what Joe mentioned during the lectures, is factor, don't cancel. And if you factor this, what this becomes is negative 2x. This becomes negative 2x times x squared minus 1. Or, excuse me, 2x squared minus 1. And this leaves us with 3 possibilities. We could have that x equals 0, and if x equals 0, because x equals negative y, that means y equals 0. We could have, again, x equals 1 over root 2, in which case y equals negative 1 over root 2. Or we could have x equals negative 1 over root 2, in which case y equals 1 over root 2. And if you look at these two, and by the way, there is a more succinct way of writing this, which is a little less ambiguous than the plus or minus thing before. You could also write this as x equals plus or minus 1 over root 2, and y equals minus plus 1 over root 2. And if you do it this way, this really emphasizes that x and y have to be of different signs. Their absolute value is the same thing, but they have to be of different signs. It's a little trick, a little notational workaround. So that's finding them. Now let's classify them. So fxx, that's, again, constant. That's 2. Fyy becomes 12y squared. Fxy, in this case, is again constant, and that becomes 2. So d, in other words, is 24y squared minus 4. So if you take d 0, 0, that's negative 4, which is negative. And then d of, I'm going to do our little trick, plus or minus 1 over root 2 minus plus 1 over root 2 ends up not mattering because you're squaring y squared. So this becomes 24 over 2 minus 4. I don't really care what that number is, by the way. It's positive. That's all that matters to me. That's a sort of a funny looking 4, but that's a 4. Point is, that's a positive number. And because it's positive, we can now check fxx at plus or minus 1 over root 2 minus plus 1 over root 2. But it doesn't matter what that is because fxx is always 2, which is positive. So the upshot of all of this is that 0, 0 is a saddle. And plus or minus 1 over root 2 minus plus 1 over root 2. These 2 points are two different local minima. So there's our solution. All right, let's do, let's see, how am I doing for time? Let me do a couple more of these. So, because you can't, the best way to do these is just to practice as many as you can to see all the different ways that things can happen. So, because I really like these problems, and the reason I really like these problems is because they're very puzzle-like. It's very much like a puzzle to try to, figure out how to solve as many different kinds of systems of algebraic equations as we can. And that's not easy, by the way. There's no general way of solving systems of algebraic equations, but you got to be a little bit creative with some of them, and that's what we're working on, is working on puzzle solving abilities. So what if we have fxy is equal to x cubed minus 3x plus 3xy squared? Okay, well, fx, we take that derivative, again, for finding them. 3x squared minus 3 plus 3y squared is equal to 0. And fy, meanwhile, is 6xy. And that has to be 0. Now we can rewrite this first equation to give us x squared plus y squared equals 1, and the second equation to give us xy equals 0. Okay, so clearly the critical points live on some circle because of the x squared plus y squared equals 1. But what about this xy equals 0? Well, again, that tells us that one of two different things is going to happen. That tells us there are two possibilities. Either you have that x equals 0, and if x equals 0, that means y squared equals 1. So we're dealing with the points 0 and plus or minus 1. Or you have y equals 0, in which case the same basic thing is going to happen. X squared equals 1, so that leaves us with plus or minus 1, 0. With all that in mind, that's how we found the critical points. Let's classify them. fxx, we take the second derivative with respect to x. 6x is fxx. fyy is again 6x. And fxy is 6y. So d is 36x squared minus 36y squared, which is, in other words, 36x squared minus y squared. So d of 0 plus or minus 1, in this case you can confidently do plus or minus 1 since we're squaring everything. That's going to become negative 36, which is negative, obviously. Now, but here's where it gets a little complicated. d 10 is 36, and d negative 10 is also 36. But the reason I did these in different cases is because f10 is a positive number, but f negative 10 is a negative number. It's more specifically, it's negative 6. So you've got all three different cases here with this problem. So in other words, we can tell that 10, because the I made a mistake somewhere. That's not f. What I meant to say is fxx. Fxx. There we go. Whoopsie. So d of 10 is going to be a local minimum. Negative 10, local max. And 0 plus or minus 1 are saddles. So there's a solution. I'll do one more of these. So actually, I'll do only one more. I really like these because because I like the pulses, like I said. So I don't know why I wrote that. So let's consider fxy to be x to the 4th minus 2x squared plus y cubed minus 3y. What does this come out to? Well, it's going to be fx. Sorry. Four x cubed minus 4x. Again, factor that, you get 4x times x squared minus 1, that's 0. Fy is 3y squared minus 3, which is 3 times y squared minus 1, which equals 0. And we see that there are a whole bunch of different things that can happen here. We know that, in particular, we have x is 0, 1, or negative 1, and y is going to be 1 or negative 1. And it can be any combination of these possibilities. So that leaves 6 possibilities in total. There's 6 different critical points. Now, if we take the second derivative, that's going to become 12x squared minus 4, or in other words, 4 times 3x squared minus 1. Fyy is 3y squared, not 3y squared, 6y. Fxy is going, but fxy in this case is just 0, because neither of them depend on x or y in particular. So d, for all these reasons, d is going to become 24 y times 3x squared minus 1. So d of 0, 1 is negative 24. D of 0, so here's how we can say this. So d 0, negative 24, which is negative, that's a saddle. D 0, negative 1 is going to be 24, which is positive. But fxx, 0, negative 1, is negative. So that's going to become a local max. D 1, 1 is 24 times 2, so 48, which is positive. And then fxx, 1, 1, is 4 times 2, is that's 8, which is positive. So that's the local min. D1, negative 1 is same whole story, but negative 48, which is negative, which is the saddle. D negative 1, 1. Now the good news is that D negative 1, 1, it's pretty much the exact same thing as before because x is being squared in this case. So D negative 1, 1 is again 48, and fxx, negative 1, 1, is 8, which is positive, so local min. And D negative 1, negative 1. In this case, same story. That's going to be negative 48. Or will it? Yeah, it will. It will. Negative 48. Which is negative, which is a saddle. So here are our solutions. Huzzah. So, all right, so great. So I'll stop here. just to point out once again that the only way to get better at these kinds of systems of equations things is to just practice a whole bunch of them, because these are really puzzles. You really there's not really an algorithm to solve these things. There are a few common strategies, though. The most important one is to get used to factoring these things. Try factoring as much as you can and set them equal to 0. If you factor something and set it equal to 0, then that tells you that only a handful of things can happen. So that helps you whittle down your possibilities. All right, thank you, everyone, and good luck, and I will see you when I see you.